Good afternoon, everyone. Welcome to day 3 of solving optimization problems. I think we've looked at a total of 4 different examples so far. We're going to look at examples 5 and 6 today. Example 5 is dealing with the design of a soup can. In fact, this is the same problem that I discussed with you a couple of days ago, where we want to try to minimize the cost of materials. And you want to design in this question a can that holds 384 milliliters of product. The first thing that we need to remind ourselves of from probably junior high is that the unit of a milliliter is a unit of volume, and it's equal to 1 cubic centimeter. Now, when we say that the can has to hold 384 milliliters of soup, that 384 milliliters is the volume. And the volume of a cylinder is equal to pi r squared h. And that's on your data sheet that I've given you. And if you don't have a copy of that data sheet, I've put one in our class folder, in our shared folder, so you can pick up a copy from there. And this 384, regardless of how we design the can, has to be the volume, which means, everybody, that this 384 equals pi r squared h is the equation of constraint. And if you can remember back a few days when I talked about this problem, I believe I showed you 3 different pictures of 3 different soup cans. And when the radius was quite small, the height was quite large. And you can see from that equation that that has to be the case. If the radius is large, you need a small height to get 384. If the radius is small, you need a large height. So there's some kind of relationship there between r and h. Now, what is it we're asked to minimize? We're asked to minimize the cost of materials. And the cost of materials is directly related to the surface area of the can. So the area of a cylinder, top and bottom, is 2 pi r squared, plus the area of the side turns out to be 2 pi r h. And that's a formula for the thing area that we want to optimize. But remember, what we would prefer, it's not even a preference, what we need is we need area as a function of only one variable. And in that equation that we have, area is defined in terms of radius and height. We want it only in terms of radius. We want to get rid of the h. I suppose you could get rid of the r's in the equation and leave the h, but since there's 2 r's, it would require twice the effort to get rid of them, so I'm going to eliminate the h. And I'm going to do so by taking my equation of constraint and rearranging for h and getting h equals 384 divided by pi r squared, and h is 384 over pi r squared, which means h in the equation can be replaced with 384 over pi r squared. That's going to give us that the area of the can is 2 pi r squared plus 2 times pi times r times the height, and the height is 384 over pi r squared. Same thing that I've been trying to reinforce to you ever since we learned about differentiating. You want to simplify anything if you can before you differentiate it. And that second term in my area formula can certainly be simplified. Area equals 2 pi r squared plus 2 times 384, I believe, is 768. The pi's cancel, and I'm left with r over r squared, which is r raised to the negative 1. Now we're ready to differentiate that. Remember, with max-min problems, you differentiate the dependent variable with respect to the independent variable. In other words, it's not differentiated with respect to time. There's no implicit differentiation here. I get 4 pi r minus 768 r to the negative 2. And again, we always want to factor expressions to make sense of them. I can factor a 4 out of each of those two terms, and I should factor out the lowest degree on the variable that's common, which would be r to the negative 2. It looks like I'm left with pi r cubed minus 768 divided by 4 is 192. Just wanted to double check that, which means we can finally write our derivative in simplified form. dA dr is equal to 4. The 4 is raised to the 1. The 4 is not raised to a negative exponent, so the 4 stays on the top. We have an r squared on the bottom, and then we have pi r cubed minus 192. So what are our critical values of r? Well, we have to take the numerator and ask ourselves what values of r make it equal to 0. Well, if I start to rearrange this, I get r cubed equals 192 over pi, which means we have a critical value of r of the cube root of 192 over pi. And then for the bottom, the critical number for r equals 0. We're still solving max-min problems where you can eliminate every critical number from the list, and that means we're still solving max-min problems that do not require the use of a first derivative chart. That last critical number, whatever the cube root of 192 over pi is, that is the optimal radius. So the optimal dimensions, which means the dimensions that are going to minimize the surface area, would be the radius is equal to the cube root of 192 over pi. And remember that we have already developed a formula for h. H was pi r squared. Pardon me. H was 384 over pi r squared from our equation of constraint, which means that h is 384 over pi times the square of the radius. Well, the radius is 192 over pi to the third, so if I square that, it's 192 over pi to the 2/3. I'm not a big fan here in this particular case of simplifying that height. You could certainly, if you wanted to, write this as pi to the 1 on the bottom, and then on the bottom you have pi to the 1 divided by pi to the 2/3. You could start whittling that down to something simpler. What I'm interested in teaching in this course, given the conditions that we're living with right now, is how to get answers, how to do the calculus. Simplifying that expression for h is an exercise in grade 10 and 11 math, and I don't want to worry about it. So let's put 192 over pi taken as a cube root into the calculator, see what we get. 192 divided by pi, and then I have to take the cube root, which is raised to the 1/3. I get 3.9 centimeters approximately. And then we are going to put that into our formula for h. I'm just going to use this formula. I'm not going to worry about typing in that whole mess. So I'm going to take 384 and divide by, in brackets, pi multiplied by the radius squared, and I get for a height approximately 7.9 centimeters. It's interesting that if you were to go to your cupboard in your kitchen and find a soup can with a volume of 384 milliliters, that these dimensions that we found do not match the dimensions on the can. And the reason is that there is a difference in cost for the materials for the top and the bottom of the can compared to the sides of the can. And I'm pretty sure that your next assignment, which will contain a number of max-min problems, is going to include a problem where you have to take that into account. But if I told you that the top and the bottom of the can cost, I'm just going to make up a number, if the top and the bottom of the can cost 5 times as much to manufacture per square centimeter as the side, then all you would do when you solve this problem is you would rewrite this, and you would maybe write something like area in relation to cost would be 5 multiplied by 2 pi r squared plus 2 pi r h. So what you would be doing is you would be multiplying the term that takes into account the area of the top and the bottom by 5, because I've told you the top and the bottom material is 5 times more expensive than the material used for the side. So you might need to use that for the assignment that you're going to be getting shortly. Anyway, the answer to the question in terms of rounded numbers is it's approximately 3.9 centimeters for the radius and 7.9 centimeters for the height. Let's take a look at the next question. And when you first encounter this question, we'll read it in a second in detail, and I'll dissect it for you. It looks an awful lot like a related rates question, but it's not a related rates question. A related rates question would be asking something like, at what rate is the distance between the ships changing? This question is saying, when are the ships closest together? So I want to start off by impressing on you that what we're really looking at here is some kind of relation where time is the independent variable and the vertical variable or dependent variable is a distance between two objects. We want a function for the distance between these two ships as a function of time. So distance between them is to be minimized. So what does this look like? It looks, as I've said, suspiciously like a related rates problem. So let's take a look at what's going on here visually. At a particular point in time, it happens to be 2 o'clock, there is a boat that starts off at a dock and it travels north. So the dot at the top of my diagram here represents where that boat is at some later point in time. We're also told that at 2 o'clock there is a boat that starts off to the east of the dock. So this boat starts here, and this distance is 20 kilometers. But that boat that starts off 20 kilometers east travels west. So this boat is going to travel in this direction, and this is where it will be at some later point in time. Don't forget that 20 kilometers is the whole distance. I need to label on this diagram this distance as being d, because that's the distance between the ships or the boats. One of the boats is here at a point in time, and at that same point in time the other boat is here. We need to identify the distance between the boats because that's what we need to minimize. Now the next thing we need to do is come up with an expression for this distance that the boat that's traveling north has traveled. We're going to do that by using a bit of science. Speed equals distance over time, which means distance equals speed times time. And the boat that was traveling north was traveling, I believe, at 12 kilometers per hour, which means that that distance it travels is the speed that it's traveling times the time. This distance that the other boat travels is its speed times its time, and it was traveling at 18 kilometers per hour, so that is 18t. And I think you can see where this is going. We're going to come up with a formula for the hypotenuse, which is the thing that we want to make as small as possible. And it's going to be the Pythagorean Theorem, d squared equals 12t quantity squared plus 20 minus 18t quantity squared. If the entire distance that I've labeled with green, and I'm going to really highlight it for you here, if this entire distance is 20, then this distance must be 20 minus the 18t. And now I'm going to explain something that if you follow this and understand it, it's going to make your life very, very easy from here on in with max-min problems if there's a Pythagorean theorem. If you wanted to, and I'm going to tell you I don't think you want to, so I wouldn't write this down if you're writing all of this in your note package. If you wanted to, what you could do is say that since I want to minimize d, I need to take 12t quantity squared plus 20 minus 18t squared and square root it to get d. Here's the difficulty with that though. If you now differentiate this, you are going to have a mess to work with. And I'm going to tell you that there is a shortcut to this, and it's to say that if d is as small as possible, then the square of d will be as small as possible. So what I'm going to do is rewrite this equation and write it as s, and the s in my mind stands for the square of the distance. Once again, if the distance is as small as possible, the square of the distance will be as small as possible, which means that this can be the function that we worry about differentiating. We're going to find ds dt, which will be the derivative of the square of the distance with respect to time. And whatever time gives us the minimum square of the distance will be the time that gives us the minimum distance. If that doesn't make sense to you, then you might have to do this. It isn't maybe that you might have to. You might not realize that you can take a shortcut and you might do that middle one instead, which is going to cause you a little bit of heartache. All right, let's continue. By the way, when you take a look at this, this is my eyeball. When you take a look at the thing we're trying to differentiate, it's quadratic. So the derivative will be linear, and it's going to be very easy to find the critical value. But I would, without a doubt, simplify this first. 20 minus 18t quantity squared. Don't forget that when you're squaring a binomial, like 20 minus 18t quantity squared, it's 20 minus 18t multiplied by 20 minus 18t. So 20 times 20 is 400. My outer term will be 20 times negative 18t, which is negative 360t. My inner will also be negative 360t. And my last will be 18 times 18. I'm embarrassed to say I don't know what 18 squared is. I want to say it's 384, but I guess we'll find out. 324, so plus 324 t squared We can simplify that further by taking the 324 t squared plus the 144 t squared to get a nice tidy quadratic function of s equals, what do we have? That's 468 t squared minus 720 t plus 400. I'd better just check that. 324 and 144 is 468. We're okay. Now we can find ds dt, which is 2 times 468 times t, which is 936. I will check that on my calculator in a second. T minus 720. We're okay. You know, you get a derivative that's linear. I wouldn't even worry about factoring this. What we're interested in is when this is equal to 0, because that's going to lead us to a critical value. So I can rewrite this as 936t minus 720. Pretty basic linear equation to solve. This is equal to 0. 936t equals 720, which means t equals 720 over 936. Again, this is a critical time. Since it's the only critical time, that means it's the time that optimizes the situation, which means the distance, well, let's stop for a second. S is as small as possible at that elapsed period of time. But since s is the square of the distance, if s is as small as possible, so is the distance, which means the minimum distance corresponds to a time of 720 over 936. Well, we don't walk around talking about time as a fraction, so what I'm going to do is calculate what that is. 720 divided by 936. Our time would be in hours because our speeds that we used were in kilometers per hour and our distance that we used was in kilometers. So 0.769 hours after 2 o'clock is when the ships are closest together. If I multiply that by 60, I see that it's 46 minutes, which means, I just want to check, I'm pretty sure it was 2 p.m., which means that this time where they are closest together is 2:46. And I guess if you wanted to get really fancy, we could subtract that 46 minutes and take 0.1538 minutes and multiply by 60 to get it into seconds, so it's about 9 seconds. I mean, you're not landing people on a planet here, so I don't know that we need to be this precise. However, this is the time when the two ships or boats or whatever they are will be closest together. So that's it for today. Not a very long lesson, but a couple of different kinds of problems that you need to give some thought to. Your assignment is only 2 problems on page 190, number 12 and 17. I think it's about time for many of you to branch out and to start trying some of the challenge problems. We will not in any way be able to look at every type of example within the lessons. Even if we were still in class, I would never get to every type of example. These challenge problems, by the way, are problems that if everything was back to normal and we were teaching in the classroom, in the school, these challenge problems would not be considered challenge problems. They would be problems that you would be expected to know how to do. So there's certainly things that you would encounter next year in post-secondary. Tomorrow we have a Google Hangout in period 4, and then on Friday we're going to be finishing off all of our optimization work, and on Friday you will be getting your second assignment to be turned in to me. I hope that made sense to you, and I hope you have a great rest of the day, and we will talk to you soon.